Okay, guys, let's continue with some kinetics videos. We're still going over the half-life formula and the first order and second order integrated rate laws. Let's continue with number 5 here, and let's read the question. The thermal decomposition of phosphine, which is pH 3, to phosphorus and hydrogen gas is a first order reaction with a half-life of 35 seconds at 680 degrees Celsius. Well, when we're reading this, there's a lot of information here, but we should really focus on the important information, which is letting us know that it's a first order reaction. And whenever I see that, I think of the first order integrated rate law, which is the natural log of A at time t. We have a negative slope, so kt, plus the natural log of A at time 0. That's our first order integrated rate law when it's in expanded form. And if we were to consider also another equation we're responsible for, which is the half-life equation for a first order rate law, which is the natural log of 2 over t equals our rate constant k. Well, now we really have our two equations that we're responsible for, and we can look at the equation, or rather the question, and figure out which one we're going to be using in this particular question. So the first order reaction with it, and they give us the half-life here and the temperature. Calculate the rate constant for this reaction. Well, we could use the first order integrated rate law. However, remember that in the previous video we derived the half-life formula, which is this guy right here, using the above equation. So because we have this equation in front of us, let's just utilize it and get this answer fairly quickly. So we're determining the rate constant for this reaction, so let's just plug it in. So the natural log of 2 over time, which our time is going to be given to us, which is 35 seconds. So it's 35 seconds, and that's going to be really quite it, because we're going to solve for our rate constant right away. So let's figure out what that is. So we're going to do the natural log of 2. We're going to divide that by 35. And let's see what we get. So the answer I got was 0.0198. And that's going to be our rate constant for this. Well, we should take into consideration the significant figures given this problem. And it looks like we have two significant figures, so I'm going to round to this 9 here because there's a number greater than 5 to the right of it, so it's going to be 0.020. That's going to be my rate constant for this particular problem. Great. Okay, so let's continue with this one, part B. Calculate the time required for 95% of the phosphine to decompose. Okay, so because this isn't a half-life equation, we're going to be using the first equation that I wrote down, this integrated rate law. So I'm just going to select it instead of writing it all over again. Let's put that here. Okay, so now we have that written here. Now let's look at this question. Calculate the time required for 95% of phosphine to decompose. Well, because we're using this equation right here, how about we just solve for t, this t right here, and then we can plug in whatever the values that we have. So let's figure that out really quick. So if we were to subtract over this natural log of A initial to both sides, okay, well, I would have this new equation, A times T minus the natural log of A and times 0. And if we were then to divide by K, I would be able to solve for T. So that's just how we're solving for a variable like we've done in any algebra class. And now we can plug in our values that we got in the previous problem and get the given values that we have right now. So let's take a look. So let's see. So calculate the time required for 95% of phosphine to decompose. Okay. Well, if 95% of the phosphine decomposed, let's just start. Let's imagine we had, you know, a 1 molar concentration of our original starting point. Well, if 95% decomposed, that would mean I have only 5% remaining after the time has passed. So what would I plug into my values here? Well, for my A at time t, that's the time that it would take for 95 to compose. So that would be the natural log of, instead of 95, we're going to put 0.05% to decompose. Because I mean, rather, that's how much I have left after 95% has gone. I'll have 5% left. And if I convert that to a decimal, I'll have 0.05 left. Now let's subtract that with the natural log of what I started with, which was, let's just say, we said our starting point was 1. So let's put that as the natural log of 1. And divide that by our rate constant, which we found out before, which was the natural log of k. So ln of k, that's going to be, or rather just negative k, that's negative 0.020, which is equal to our time for this thing to decompose. Let's take a look. Well, remember that the natural log of 1 is going to be equal to 0, so we actually don't really need that component. So now we just only have 2 things to compute. So let's do that really quick. This would be the natural log of 0.05 over a negative 0.020. And if we get our answer, let's see. Well, I have my time here, and that's going to be in seconds because our rate constant had units of seconds before, reciprocal seconds. So when we solve for this, it's going to be 149.787 seconds. Let's accommodate for significant figures for 2 sig figs. So my time is going to be 150 seconds. Great. So this sounds like a nice round number, and it also makes a lot of sense, considering that it took 35 seconds for half of it to decompose. And if we were to kind of extrapolate that to having 5% remaining, 150 seconds doesn't sound too bad, because it would be, in order for a quarter of it to be left, that would be 70 seconds, and so on. So we keep adding that. So yeah, 150 seconds sounds about right. So hopefully that was very helpful. This is just another example of using the integrated rate laws. And while I may not be able to get an example for second order reactions, the overall idea is the same. Manipulate this equation, the integrated rate law, to your advantage, and solve for the variable of your choosing. That's kind of the appeal of these rate laws, is that given the question, evaluate which variables you have, and then continue with the problem and solve for it, by isolating it using your algebra skills, and then plug in the necessary values. So again, I hope this was helpful. We're probably going to continue on with maybe another example, and then we'll get on to catalysts and even the Arrhenius equation. So